In this lecture, let's continue the discussion of insulin. Here we focus on what triggers its release, and then we gradually move on to talk about glucagon and how that is released and compare the two. All right, so what triggers the release of insulin? High levels of nutrients, that is, soon after a meal, increasing levels of glucose and amino acids are a trigger for the release of insulin. Okay, now yet another factor that could release insulin is activation of parasympathetic system. Okay, so think about it like this: eating or thinking about food even can activate parasympathetic division, and that would then trigger the release of insulin, basically preparing the body for the arrival of nutrients. Okay, now the opposite of this effect is sympathetic activation. If sympathetic system is activated above and beyond normal, that's when you have epinephrine released, and epinephrine inhibits the release of insulin. It makes sense when you think about when the sympathetic activation is increased. Fight or flight response is where the body wants the skeletal muscle, the respiratory, the cardiovascular systems to be activated above and beyond normal to deal with this new situation, and therefore digestive and renal functions are ignored. Blood supply from these two systems is shifted to skeletal muscles, and then the respiratory and cardiac systems. So these are the key components. One is high levels of blood glucose, high levels of amino acids, activation of the parasympathetic division are the triggers for the release of insulin, whereas sympathetic activation has the opposite effect. All right, so with that information, we will move on to look at the exact action of insulin. Here we look at 3 different cells and how insulin has different roles or different types of effects at different targets. Hepatocyte, so in other words, at the liver, okay, insulin promotes the storage of glucose. Okay, so first it stimulates the uptake of glucose, meaning moving glucose from the blood into the liver, and that is glucose uptake. And now its phosphorylation, that is to convert glucose to glucose 6 phosphate. And then eventually, depending upon the levels of glucose that's available, excess glucose is all going to be stored in the form of glycogen, so increased glycogen synthesis. Insulin being an anabolic hormone, it promotes synthesis of storage type of molecules. Proteins, glycogen, lipids are constructed in the presence of insulin. Here, you just focus on glucose. So insulin makes glucose be converted to glycogen within the liver. And at the same time, it's important to note that insulin prevents the breakdown of glucose. So inhibits the breakdown of glucose, promotes the synthesis of glycogen. Then similarly, increased lipogenesis, meaning production of different types of lipids within the liver, and then again prevent the breakdown of lipids, inhibition of lipolysis, and then increased protein synthesis. Remember, there is amino acid released during digestion and absorption that is used in the production of one or yet another type of protein. So all these are possible in the presence of insulin within the liver. What about adipocyte, that is in the adipose tissue? What message does insulin give? Okay, so adipocytes have GLUT4 transporters. They are the ones that are dependent on insulin. Now, in the presence of insulin, GLUT4 transporters are busy transporting glucose into the adipocyte. That's what you refer to as glucose uptake. And this glucose is now converted to lipids, triglycerides. Initially, glucose is converted to pyruvate, pyruvate converted to acetate, acetate is converted to acetic acid combines with the coenzyme A, aceto-CoA, then gradually acetic acid is, if aceto-CoA is not used for energy purpose, then acetic acid combines with other acetate molecules to become a fatty acid, and fatty acids put together will now be combined with the glycerol, and that's how you have lipid synthesis that happens within the adipocyte. Okay. Now, what about at the muscle cell? Well, muscle fibers also have GLUT4 transporters, meaning insulin dependent type of transporters. So in the presence of insulin, they will be moving more glucose into the cell, and then this excess glucose is now going to be converted to glycogen. Okay, any excess glucose is converted to glycogen. Okay, now similarly, protein synthesis occurs and some lipid synthesis occurs. Muscle cell is where the storage of glycogen is more abundant than the storage of lipids. All right, so that is how the muscle cell, under the influence of insulin, can use glucose to make glycogen, and then amino acids could be used in the production of proteins, and then lipids are constructed as well. Okay, with this, let's move on to talk about glucagon, which is the antagonist of insulin. Okay, so if you know the functions of insulin, which you do now, you just have to think about the opposite for glucagon. So let's begin. Glucagon, first of all, is released in a condition where you have less glucose available than normal in the blood. So that's the condition when glucagon is released. Glucagon is released when glucose levels are below normal. Okay. So the goal of glucagon is to increase blood glucose levels. So it inhibits the uptake of glucose. Inhibits the uptake of glucose, meaning you do not want to move glucose to the cells, but to leave it in the blood. And also inhibit the breakdown of glucose. So inhibits glycolysis, okay? Promotes gluconeogenesis. Gluconeogenesis is the synthesis of glucose from non-carbohydrate molecules, amino acids, pyruvate, lactate, etc. So that is promoted in the presence of glucagon. Most of these events occur at the liver. Uh, Gluconeogenesis, glycogenolysis are all things that occur at the liver, and that is influenced by glucagon. Okay, increased lipolysis, that is, you want to break down lipids so that lipids can be used as sources of nutrients, and fatty acid can be ultimately used in the synthesis of new glucose, gluconeogenesis. And it also promotes lipolysis, that is release of fatty acids, and inhibit lipogenesis. So it prevents or interferes with the production of new lipids. And that's how you would have increased ketone bodies, okay? That's because you're breaking down these long chain of fatty acids, and partially digested fatty acids are what you call as ketone bodies, okay? So here is a beautiful summary of what happens when blood glucose levels are greater than normal in the blood, and then blood glucose levels are less than normal. So they have made up some numbers. Here is blood glucose level that's above normal, 160 milligram per deciliter. And now you have to think about the release of insulin by beta cells. And when insulin is around, what it does is already discussed, but it's a great review for us. Triggers body cells to take up glucose from the blood, utilize in cellular respiration, that is in the production of ATP, inhibits glycogenolysis. And glycogenolysis is the breakdown of glycogen, and that is prevented and inhibits gluconeogenesis. Again, gluconeogenesis is the production of glucose from non-carbohydrate sources, and that you do not have to do because you're trying to move glucose into cells but not to release it back. All right. Therefore, blood glucose levels would drop and situation would be back to normal. A very good example of homeostasis, that is, how everything is maintained at a steady state. When levels go up, you bring in insulin and you remove excess glucose from the blood and move into the cells, and blood glucose levels drop. Now we will look at the other half of this picture. The situation is where blood glucose levels are lower than normal, 50 milligram per deciliter. Okay, the normal range, by the way, is 70 to 110 milligram per deciliter. All right, so when blood glucose levels are low, you would release glucagon from the alpha cells of pancreas. Okay, now what does glucagon do when it's present is summarized here. Inhibits body cells from taking up glucose from the blood and utilizing it in cellular respiration. So you do not want to move glucose into the cell. So you want to leave it in the blood cell. Stimulate glycogenolysis, that is the breakdown of glycogen. All right, stimulate gluconeogenesis, that is the production of glucose from non-carbohydrate type of sources. Okay, so that is a great summary of all the details you have been working on regarding insulin and glucagon. Here is a beautiful summary of, again, two situations. One is anabolic state and the other one is catabolic state. Okay, anabolic state is the building process and catabolic state is the breakdown process. Whenever you have eaten a meal, that is the absorption state, post-absorptive state is how you could call it. And anytime you have no food to deal with, that is the fasting state. So I'm sorry, post-absorptive state is the fasting state also. Absorptive state is when you're dealing with food. Okay, so anabolic state, is absorptive state. Catabolic state is post-absorptive state, or also referred to as fasting state. So anabolism is what you're talking about here. You would have more insulin at that time because you have nutrients being released, which have to be processed, and there is going to be less glucagon during that time, right? And then fuel source is diet, so you're processing meal, and what all can happen here is synthesis of glycogen, synthesis of lipids, synthesis of proteins. A catabolic event is when you have to think about post-absorptive state or a fasting state, when there will be less insulin and more glucagon, and that's where you're tapping on the storage depot of nutrients. So that's where you expect glycogenolysis, lipolysis, proteolysis, ketogenesis, etc. Okay, so good. So that is what you expect at two different states in the body. Let's talk about factors that increase glucagon release. So what makes you release glucagon? So as I mentioned, low levels of blood glucose increases glucagon release. Yet another interesting fact is increased levels of amino acids. Please recall that increased levels of amino acids release insulin. Increased levels of amino acids can also release glucagon. Why? If you have a diet that's mainly protein but no carbohydrates, then because of low carbohydrate situation, you would probably start releasing glucagon, okay, even though amino acid levels are high. Okay, so carnivorous meal, protein-rich food can cause hypoglycemia, and that's what causes the release of glucagon. Remember that insulin secretion is increased during parasympathetic activation. Here it's the opposite. Increased sympathetic activation increases the release of epinephrine and therefore increased release of glucagon. All right, increased growth hormone increases glucagon, increased cortisol increases glucagon. So these hormones, a number of hormones, all come together to make sure that there is sufficient amount of glucose in the blood to prepare the body to cope with stressful conditions, stressful situations. Okay, so those include cortisol, growth hormone, epinephrine, all of those promote the effect of glucagon. Okay, now what we are summarizing here is that which hormones are involved in decrease of blood glucose levels versus the hormones that are involved in the increase of blood glucose levels. We just went over it in the previous slide. Insulin is always going to be an anabolic hormone. It moves glucose from the blood into the cells to allow the synthesis of glycogen. Okay, whereas these other hormones like glucagon, epinephrine, growth hormone, and cortisol will always lead to the breakdown of glycogen, so that there is increased levels of glucose in the blood. So they're all looking at one thing, that is how to increase blood glucose levels. That is, typically in the normal range. However, insulin has the opposite effect. All right, so this is the end of our discussion of insulin and glucagon in a normal situation. Thank you.